right? So this is today. Oh, I handed out your the sheet that kind of gives you hints about what's going to be on your next exam on Wednesday. I'm going to record something and post it by Sunday. So today I'm hoping to finish up this part. We'll see. The lab write-ups are due today, but if you don't get them done, just keep plugging away and get them turned in. I want 2 and 2, or all 3 or 4, but I need to at least have 2 by midnight tonight, okay? And so I'm kind of liking the way this is working. You have a few days then until I need to put in midterm grades. When midterms comes, and if I still don't have 2 labs from you, I'm going to have to put a 0 in any space that I don't have of the 2. The whole course is 2. Yes?
So we're finishing up everything today?
So we're finishing up telescopes, and then we're going to come back to the moons on Monday.
Yeah, okay.
Yep. So that leads me to Monday. Monday, we're coming back and hitting the moons. And then Wednesday's your exam, and Friday, no classes anywhere, unless they're online. They just keep plugging away. So no classes, this class won't meet. And then there's this meteor shower, I think I've mentioned. I'm really excited about it, but the logistics for that day for me, I really can't be 2 places at one time. So I have to be in West Burlington that day. So that morning won't work for me to come do morning lab. But not to say that you all can't, as a group or individually, go find some dark skies. These skies wouldn't be good for meteor showers. So between now and then, I'll see if I can find, if I was local, I'll try to say where I would go. I'm kind of leaning towards over the river, and there's like I'm trying, anyway. So anyway, I'll try to see what I can come up with. All right. Dun, dun, dun. So has anybody ever in here kind of played around with a magnifying glass? And yeah, why am I not surprised? And I kind of tease, you can actually kill ants or start a fire with a magnifying glass. And this is kind of how this works. What you do is you kind of take the ground and you go up and down until you get the nice concentrated blip of light. What you have done is just actually come up with what we call the focal length of that magnifying glass. You've concentrated all the light to a particular point. And that's what telescopes do. So this one, okay, this one uses lens. And it actually has a double convex, so it's fat here. We talked about refraction. Refraction is bending of light. So that's all that this fancy glass is doing, is bending light actually twice, and it's bending it back to a focal point, where you kill your ants, okay? Then what happens is, so the focal point might be about here or so. Then the image comes out here, and it is what I call unpacked by the eyepiece. So there's an eyepiece here. Now, there's a focal length here to the eyepiece, and there's a focal length here to what we call the objective. So I hope this kind of looks like that. So you can kind of see the lens here, the light coming through, it's being refracted and converging to a point. There's where you kill your ants. Here it's unpacked, and here's the eyepiece right here. So that's a refractor, uses lenses, refractor. There's too many R's here. Refractors uses lens, a reflector uses mirrors. Okay, so this would be a reflector. Now I'm gonna show you, this is this type of reflector. So I'm gonna bend this down again. You guys told me there's a mirror. You guys see the little, you see the little circle? Okay, on the other side of that little circle is another mirror, okay? And that mirror is actually taking the information and shooting it out to the eyepiece. So that's it. So primary mirror, this is the primary mirror. So this is the primary mirror back here that you looked at. The secondary mirror is right there, and it's shooting out the side. This is called a Newtonian design. Newtonian design. Well, there's other ways to kind of configure how are you going to get that reflected image. This is a Cassegrain design. It's really common. The school has one of these too, where here's your primary mirror right here, and it goes back to a secondary mirror. Instead of going out the side, it goes back down and it comes out the butt of the telescope. Okay, so here's your eyepiece. If you've been out to the observatory, this is that 16-inch, that one that has mirrors. The 16-inch reflector is a Cassegrain. It's a great type of design too. And these are both reflecting telescopes. Well, here's another reflecting telescope. It's called a prime focus, and this is one of my favorites. It doesn't have an extra mirror to shoot it anywhere. Basically, if I could draw a little stick man, I'd put a little stick man right there. He basically sits there. It's prime focus. I think that's kind of cool. So telescopes. What do you think? What do you think by the size of that mirror? Pretty humongous. 8 meters, so I've got, this is a meter stick. Looks like a yardstick, but really it's a meter stick. Okay, 1 meter. Okay, so 8 of these in diameter. Yeah. Yeah, that's really big. I know the other day when I adopted this, the mirror was kind of grimy, so I carefully took the mirror out of its cell down here. I guess I left it in its cell. I just had to screw it out, took the whole cell out, and I read online how you carefully clean the mirror. So this is in the European Southern Observatory, Very Large Telescope. Isn't that a really nice name? Very Large Telescope, yes. Here's another telescope. This one is 5 meter reflector. So does it use mirrors or lenses? Mirrors, yep. 5 meters. So 5 of these is the diameter of the mirror. That looks mammoth. And you kind of see the dome, kind of like we had at the observatory. This one, though, is 8 meters. And the caption, I know, 8 of these. The caption says that this one kind of looks lighter. Okay, this thing right here is called the tube, the optical tube, and I really wouldn't want to hurt it, right? I'm like, but it really doesn't do anything other than kind of keep the, in this case, the secondary mirror up here and kind of suspend so we can look through the objective. Okay, this optical tube doesn't do much. This optical tube is kind of like a truss design where it's kind of open. I've seen some really neat telescopes where in order to kind of reduce the weight and they want to transport it, they just go with like this truss design. That's kind of neat. For big telescopes, 36 eyes are better than 1. Is that not creepy or what? Can you kind of see these little 6-sided little things right here? Okay, so those are little mirrors. And I'll tell you a little bit later why it's an advantage to actually have kind of little mirrors all knitted together to make one big mirror. The shape that we're after for the back of the shape of the mirror is actually a parabola. It's just kind of hard to say, a parabola, instead of a sphere. So they take these and they knit them together to make the parabola, to take all the light and come back to a focal point.
I watched this, Mythbusters episode one time where they took the hexagon mirrors and put them in a convex and then found the focal point and was trying to burn wood with it.
Right?
So it's like pretty much the same kind of curve.
Yeah, it is. It is the very similar curve. Yeah. Does anybody know where the Keck Observatory is, right offhand? It's in Hawaii. Road trip. And I've heard, what's that?
You're buying.
Right. And you might think Hawaii, that's not a very wise place because of all the water, the big water that surrounds it, right? But actually, as it turns out, it is a nice place because it's up high in elevation. This one, actually, we could take a road trip to. This is a little bit not too far from Chicago. It's at the Yerkes Observatory. So let's see. Now, refractor. So does it use mirrors or lenses? It uses lenses, yep. So as it turns out, this is a meter stick. So we have 100 centimeters, okay, 1 meter. And then over here we have inches. And so apparently 39 inches is approximately, the 1 meter is about 39 inches. So this is about how big that, the diameter of that lens is. Okay. Right up there. and here's the dome. So it's not very big. Now, it's the biggest in the world. The problem with lenses is, have you ever seen, especially in older houses, where you look in the windows and it kind of looks like the glass is kind of deformed? Yeah. As it turns out, glass over time, gravity will kind of change the shape of glass. And that's one thing with your very specifically shaped lens, that it can deform over time. So if you get much bigger than this, it's not gonna keep its shape basically over time. So that's kind of a limitation to refracting telescope. So yeah, this one's not that far away. I have friends that have gone several times. Right. Here is, this one's in Chile. You can kind of see a lot of times there's an observatory complex with multiple telescopes. Looks very remote, doesn't it? Why do you think they might want to build something in the middle of nowhere? Light pollution was what I was thinking of, yeah. Yep. This one is in the making. Again, I mean, it's like, who came up with these words? Trump? No, I'm just kidding. But really, European Extremely Large Telescope. You know, European Very Large Telescope. Can I not come up with any more words? Okay, but this one's in the making, actually. And let's see. It'll be another, use mirrors, so it'll be a reflecting telescope, 39 meters in diameter. Serious. Yeah, that's a big hairy deal. So we have two A's. We have active optics and adaptive optics. Active optics are a little less sophisticated than adaptive optics. There's too many A's, too many R's. Active optics will take the whole mirror, the whole primary mirror at the back of the telescope, and it will kind of adjust it a little bit based upon the turbulence that's happening in the atmosphere. Because as I hold my hand up here, you figure that starlight or the light from the galaxy has to go through Earth's atmosphere, come down and interact with your mirror and go back to a focal point and be seen. So if you know what the turbulence is, you can kind of change this a little bit. Now, adaptive optics, like I said, is a little more sophisticated. Instead of moving the whole mirror, remember we looked at the whole segmented mirrors, like the 36 eyes are better than one sort of thing? It literally reshapes the parabolic shape, again, to adjust for turbulence in the atmosphere. When I think of maybe both of these, but even this more sophisticated one, I think of it sending up, maybe I must have read this, it sends up a beam and basically looks at that beam through the outward beam through the Earth's atmosphere. It's like, oh, okay, I can see what the Earth's atmosphere is doing, and then it adjusts to compensate. That is so cool. Are you serious? And I have some slides to kind of talk about the Earth's atmosphere. What sort of problems does it create? So this was of the planet Jupiter, taken by a telescope on the Earth, a land-based telescope, using adaptive optics, so that more sophisticated. I double-checked this, but if you have a camera that's like a 35 millimeter, is that what I'm saying? Like the Rebel. I have a Rebel. So they have at the back of the your camera, they have like a little CCD, a little chip. And actually, all this says is anymore when they photograph celestial objects, the CCD is a lot more effective than your old-timey like film that you used to get developed. Anybody else in here have film they still need to develop? I do. Really old film. Okay, so then again, this is the CCD chip. Amazing. So we talked about cousins, and one of the cousins from visible light is radio waves. Are radio waves longer or shorter than visible light? They're longer. Yes, radio waves are longer than visible light. And this whole idea of kind of dialing, looking for different wavelengths from space, it hasn't been around all that long. So in 1932, radio